here are a few of the things that we will be looking at. These problems all look a lot like you should do u/du substitution for them. If I tried u substitution on this first one, what's the issue? So what would the u be if I tried to do this problem? Okay, and so du would be negative 2x, oops, there's x right there, plus 6. Can I put that there? I can deal with an extra x, like if my du is just 4, and there's an extra x, I can deal with that because I can solve my u for x and plug it in. I can have too many x's, right? I cannot have a du that is missing, right? Because my du here should have an x in it, and there is no x there to be found. So that would be an issue. The same thing is going to happen here. For this problem to do a u/du, you would have to do u is 8x minus 4x squared. But that would mean du would be 8 minus 8x. And am I going to be able to make that appear with just a 10 in the top? I cannot. I would have to have an x there. So that would not work. Same thing here. If I try to use the denominator as a u, then I've got all this complicated stuff in the top. Maybe you could try to do that with like a, no, it's going to be bad. I could maybe try to make the top u, but then my du is in the bottom, and there's going to, like the du of this would be 6x squared minus 2x, and I can't make that extra x appear, right? So today we're going to look at these 3 types of problems right here and how we can deal with those. The first one that we're going to look at here, we've got 12x squared over 2x plus 1 here. We could kind of do a u/du where we've got like an x and we solve it for u and we square it here. But if your numerator is greater than your denominator, okay, you can use long division, which I realize we haven't done in a long time. But let's make ourselves a note right there. If the numerator is greater than the denominator, you can use long division. So if I want to use long division on this, the 2x plus 1 goes on the outside. The 12x squared goes on the inside. And you might want to do this plus 0x plus 0 there. So if I think you do this in Math 3, I can't remember if I made you do it in pre-cal. If I did, it was once or twice. Yeah, it probably didn't have x's in it in 6th grade there. But, yeah, this is Coach Wood's Gazendas right here. Coach Wood was teaching you the Gazendas. So, so if you had that. So you got to ask yourself, what times 2x would give me 12x squared? So what times 2x will give you 6x? So 6x is going to go here. And so we got 6x times 2x gives me 12x squared. And we got to do 6x times 1. That'll give me plus 6x. Okay. So after I do that division and I multiply, what do I have to do next? Subtract. Be careful with signs on this. I mess this up so often. So this cancels. You'll get a negative 6x. And you can, that plus 0 is kind of a placeholder. You can bring it down or not. So then I got to divide again. What times 2x would give me negative 6x? Negative 3. So I'll get negative 3. And so I do negative 3 times 2x gives me negative 6x. Negative 3 times 1 gives me negative 3. Okay, what do I do next? Subtract. So that makes this like a plus and this like a plus, right? Because it changes those signs when we're subtracting a negative. This cancels. I get a positive 3. Can I divide again? I cannot. So what I've got here is a remainder. What we're going to do with our remainder is we're going to write it this way. We can take the remainder and put it over whatever we were dividing by. Okay. Are we okay here? All right. So when we do this, we've not integrated at all. We're rewriting this original expression so that we can integrate. So now what we're going to have is rather than integrating this, we will be integrating 6x minus 3 plus 3 over 2x plus 1. That whole thing will have a dx at the end of it. Now, these first two, when I integrate, if I have things separated by plus or minus signs, I can integrate them separately, right? So 6x and minus 3 are just straight power rule problems, right? Essentially what I'm doing is I'm breaking this into two parts. I'm doing 6x minus 3 dx, and then I'm working with the 3 over 2 plus 1 dx, right? I'm integrating those separately. So that first part, I just use the power rule for. I'm going to have x squared. I got to divide by the 2 out front, which will give me a 3 minus 3x. And I could put a plus c here, but we'll just put the plus c's together at the end. And so that should narrow down your choices right now. What would you throw out from this point? A and B, they're gone. These two both have that 3x squared minus 3x that we need. Then over here, what can we do for that second part? We cannot do a negative exponent because of the 2x plus 1. If it was just like a 2x, we could use a negative exponent for it. But the plus 1 is what makes it impossible for us to do a negative exponent for that. But we can do a u to u substitution. So for this, our u would be 2x plus 1. So du would be 2 dx. So we need a 2 with that dx. That 3 is in our way, so we're just going to pull it out front. Put the 3 here. But if we put a 2 on the inside, what do we need to put on the outside? A 1/2. So I'm just going to make that 3 over 2. Is that all right with you guys? Okay. So I'm going to say, actually, I'm going to fix this because it's a multiple choice. It doesn't matter. I really want to integrate those two things at the same time because I want to put their plus c's together. So like if you're doing this on a free response question, let's actually not integrate this yet. So we're integrating both of them at the same time. That's just like the proper way to do it. So I haven't integrated the second stuff yet. It's going to be 1 over u du. So when I integrate here, I can integrate this stuff as we just did is 3x squared minus 3x plus, and I'm going to have a 3 halves here. What do I get when I integrate 1 over u? Natural log of the absolute value of u, and then we'll have a plus c on the end. So it's multiple choice. It really doesn't matter on this, but to do this correctly, we want to integrate those two things at the same time so we can put our plus c's together. Technically, if you integrate one part of it and you don't put a plus c, that they're going to count that wrong on a free response. You're going to lose points for that. So we need to put our u back. So that's 2x plus 1, 3x squared minus 3x plus 3/2 natural log, absolute value of 2x plus 1 plus c, and that is answer choice D. No, it's not D. Didn't look at that very well, did I? C. What they say? What did they expect for you to do wrong on D? Not put that 1/2 in when you do your, and that would be so easy to do, right? So be careful. As long as you're like foreseeing that it's going to be 1 over u and that's just natural log of u. If it was something besides 1 over u, like if it was 1 over u squared and you were having to do negative exponents and there might be like a fraction to come up, you would need to keep working. But because we know it's just 1 over u and it's going to be natural log of u, then you'd be okay for that. But if it were like, if you had like u to the third, for example, like if I had a 3/2 and I was integrating 1 over u to the third du, that is really u to the -3 du. So that would be 3/2. I'd increase my exponent by 1, which would give me -2. I'd have to multiply back out front by -1/2. So that would change that 3/2 to a 3/4, -3/4. So in this case, it would be okay because it's just natural log, but there can be times where you probably need to keep going. Okay? All right, so when do we do this? When do we do long division? Numerator is greater than the denominator. Okay? All right, now, here you have your inverse trig integrals. Whenever we did derivatives of inverse trig, I did not make you memorize them. So I'm not going to make you memorize these right now either. You do have to have them memorized for the exam, but that's not until May 13th. So we'll worry about memorizing them whenever we get there. I don't want to spend a lot of, if you memorize them right now, I know that you will forget them. So let's just go ahead right now, and I'm going to put these on the board for us. They will stay up here, and they will be up here during the test. So we got arc sine, and of course for arc sine they sometimes use inverse sine. The one they like to put on the real exam the most is inverse tangent. That's the one they put on the real exam most often. And then I have never seen arcsecant on the real exam, but they could put it there. So we'll learn it. Although I don't even know if mine. Alright, so these will stay up here on the board for you. You will have them to use. They're more difficult. The really difficult thing about these is recognizing that that's what you need to use. So here is an example of something that we may see. Okay. If they're multiple choice, it helps, because if they're multiple choice, some of the answer choices are going to have the inverse trig in the answer choices. And that is going to make you think, wait, maybe this one is one of those inverse trig ones. I should look at those formulas. And in particular, they only use inverse sine, so that lets you think, probably this one's inverse sine, right? When these are not multiple choice, it makes it even more difficult because you don't see an inverse trig anywhere, which means it's hard to recognize that's what you're doing, because nothing about that looks like trig, which is one of the crazy things about trig in general, is how is trig integral of this. It seems crazy to me that that ends up being the integral, but it does. Trig just pops up like in all kinds of places where it has nothing to do with triangles anymore, it seems like. So, this one, if you try to do a u/du substitution, you would have to use what's under the square root as your u. What would be your du if you did that? Negative 2x minus 4. And are you going to be able to put a negative 2x minus 4 up here with that 8? You cannot, because you cannot add in an x. You can't put an x on the inside and 1 over x on the outside. You cannot do that with variables. So if you try u/du substitution, it is not going to work on this. So our answer choices give away that we're probably using this formula. The integral of du over square root of a squared minus u squared equals arc sine of u over a plus c. This, however, does not look like a number. So in this formula right here, a is a constant and u is some sort of variable expression. It might just be like an x, but it can be 2x plus 4, or it could be x minus 7, or something like that. So I don't have that right now. So what I have to do is I'm going to have to complete the square. So we learned how to complete, I'm just pulling up all kinds of old stuff that nobody learns how to do all that well whenever you're in Math 3. And that actually might be Math 2, but like you've done it. You probably could do it back then. I don't even know if you were good at it back then. But you could probably do it, but you've probably suppressed that memory there. So completing the square is going to look like this for this problem. Numerator stays by itself. This 12 is going to stay out of the way. We need it to be a squared minus u squared. So we want this to be a minus, so we are going to factor out a negative and make this x squared minus or plus 4x, and I'm going to put a plus blank right there. Okay, so when we did completing the square, one of the first things you used it for was solving quadratic equations, and like if we put a plus blank here, we put a minus blank or a plus blank on the other side as well. But you don't have an equation right here. So you can't put a plus blank right there. But you can put a minus blank over here. Because if I add a number and then subtract that same number, those cancel each other out. And whatever I started with is still equivalent there. So our goal is to have something like this. We want to have something squared, right? We want like a number minus something squared here. So what we're trying to do is we're trying to make x squared plus 4x plus blank a perfect square so that we can factor it and make it like x plus 2 squared, right? So whenever you do this, you're going to have an x right here. You're going to take, to complete the square, you take this middle number. It's like reversing a square double square, right? This middle number is your double. So you got to divide it by 2. That gives you the number that goes right here. So we'll have a plus 2, right? So if we reverse this double, x plus 2 squared has to equal what you've got in this parentheses, right? X squared plus 4x plus blank. So if I square double square this, x squared plus 4x plus 4 is what's going to go here. So you're taking this number right here and you're raising it to the second power and you get that number. Really should have done one where it wasn't 4s, where those numbers are the same. But you divide by 2, so we're dividing by 2 to get the number that goes here. We're squaring it to get the number that goes here. You guys kind of remember doing that. We did it with circles. We did do it some in pre-calc because we did it with circles and ellipses and all of that stuff there in a similar manner. We didn't solve, but we did do that. So what number should I subtract over here? If I added a 4 in here, what should I subtract?
4.
No. It is almost a 4. No. It is a negative 4. Why is it negative? When I add this 4 right here, what do I have out here that gets distributed to it? Negative, right? Whatever number is out here, which in this case is a negative 1, you've got to take that 4, you got to multiply it by that negative 1. So that actually becomes like a plus 4 because we're subtracting a negative 4. Now, if this plus 4 over here on the end, I can add it to the 12 up front, which is actually good because that gives me 16, which is a perfect square. Okay? Is everybody with me there? Okay, with the formula, this is not that bad once you get it to this point. Because what we're doing, we're just going to leave that numerator. I'm going to write that 16, I'm going to write it as 4 squared minus x plus 2 squared. So in that formula, it is du over square root of a squared minus u squared. So what would the a value be for this? Is there 4? And what is our u value here? X plus 2. So what is du? Just 1. Right, so I forgot my du over here, or dx, I'm being lazy. Right, yeah, you're correct. I like that you said that. That is 1 dx. So is this 8 right here really necessary? It's not, but since it's just a coefficient, what can we do with it? We can pull that out front. So we are going to have 8 times the integral of, I'm going to write this step, you don't necessarily have to, square root of a squared minus u squared du. If you skip writing that step, it's okay. And when we integrate 1 over a squared minus u squared du, we get, I'm going to write inverse sign instead of arc sign because that's the notation that they use. We get inverse sign of u over a plus c. And if we put, our u and our a back in, that's going to be x plus 2 over 4 plus c. And that is answer choice D. Simple. Okay? All right. Okay. 3. This one is, this one initially to me looks like a u du. But if you use x squared plus 4x plus 8 as your u, then your du is 2x plus 4. And can you just add in a 2x up here? You cannot. So answer A should be out. That is not going to be an option. And based on our answer choices, which inverse trig does it look like we're going to have? Tangent. So that formula for tangent is the integral of du over a squared plus u squared is going to equal 1 over a. I'm going to use inverse tangent notation since that's what they use here. Inverse tangent of u over a plus c. So, what we're looking at right now does not look like u squared plus a squared plus u squared, right? I've got x squared plus 4x plus 8. So, what I'm going to do, I'm going to put the 8 first. And then I'm going to put x squared plus 4x plus blank. I need to complete the square on this. And if I put a plus blank right there, I've got to put a minus blank over here, because I can't actually change the value of what I'm working with. I should still have my dx over here. So, we want to complete the square, and I've used the same numbers again, so I should have picked a different one. X squared plus 4x plus 1. I'm trying to turn this into x plus something squared right here. So what number am I going to get right here in this set of parentheses for my x plus something squared? Yes. So how did you get that, Liam? Okay. 4 is your double right here, right? So to undouble something, you got to divide by 2 to get that number. What number goes in the blank? Up here. We're going to raise to the second power. That's going to give you a 4 that you're adding here. If I add a 4 right here, what do I have to subtract over here? It's just 4 this time. Because this time I had a plus in front, right? There's just a 1 right there. So it's just a 4 this time. So I do, in fact, end up with a minus 4 out here. Actually, that 8 right there, I'm going to get rid of it, because what should I do with that 8? I should combine it with this minus 4 over here, so I'll get 4 plus here. Now, I want this to be a squared plus u squared. So I should, and I also don't really want that 4 right there in the top, so I'm going to pull it out. So I'm going to have 4 integral 1 over, I'm going to write that as 2 squared plus x plus 2 squared dx. What is my a value? 2. What is my u value? X plus 2, so du would just be dx. So this is a squared plus u squared here. So when I integrate that, I'm going to get inverse tangent of u, which is x plus 2, over a, which is 2. Oh, wait, I've messed it up. What did I do wrong? This is not the right answer. I forgot my 1 over a, because this formula has a 1 over a. Sine does not, but the other two do. So I forgot my 1 over a. This 4 out here, it's going to be right here. I got to multiply it by 1 over a, which is 1/2. So which answer choice is that going to give me? D. It is really helpful if it is multiple choice, so your answer choices kind of lead you in that direction. You have to know the formulas, and you have to know that that's what's happening. If you find yourself, Liam, doing a u-du substitution that won't work, a lot of times it might be inverse trig. But I will say that if they put inverse trig on the free response, which they do about half the time, about half of the years there's an inverse trig on free response.
Was it last year?
I don't think there was last year. Honestly, I think the free response were easy last year. I'm not going to say it always alternates, though. But if they ever put it on there, it is a highly missed problem, because it's really hard to recognize that you're supposed to be doing inverse trig there. Yeah, but what most kids do, if most kids that get this on free response where there's no answer choices to lead you in that direction, usually end up with answer choice A. They just, like, they get the du of 2x plus 4, but then they just don't put it in there, and they just make it a natural log. Like, they just try to make it work. So that's what I usually see if it doesn't have answer choices with it. So it is a little tricky to recognize those there. This is not something you're going to see tons of problems on the test Wednesday or the final exam. I will guarantee you'll see at least one of these on the test Wednesday, but it's not going to be, heavily tested there. It'll probably be one. It might be two. No more than two for sure, though. Yes, and there's a lot of Unit 6. It's a long unit. Yes. Yes, we're reviewing tomorrow. Yeah, this will be our last unit. Start Unit 7. Yeah. Yeah. Yes, we will do test corrections on Unit 6. So I will get your test graded back to you by Friday, at least. I may not get them Thursday, but I'll get them by Friday so that you have them over spring break, because I know you probably want to do your test corrections over spring break, but they will not be due until probably like the Thursday or Friday the next week. At least by then, though, because I got to get grades in. Midterm will not have test corrections on this quarter, though. I may or may not do corrections at all on midterm. All right. Okay, let's look at our last one. What should we do on this one? This one's long division. This is not inverse trig. This one's long division. So let's do another practice with some long division. 3x squared plus 2x plus 1 plus 2. All right. So what times x gives us 3x squared? 3x. Then we have to multiply 3x by x plus 2. So 3x times x is 3x squared. 3x times 2 is 6x. Okay. Then we need to subtract, which will cancel our 3x squareds. And we'll get negative 4x. And we'll bring down our 1. Okay. Then we need to ask ourselves, what times x gives us negative 4x? That will be negative 4. So negative 4 times x is negative 4x. Negative 4 times 2 is negative 8. We are subtracting, which actually is going to look like adding here because both of those things are always already negative. This cancels. We'll get a 9 right here. Okay. So this can be written plus 9 over x plus 2. So I am integrating from negative 1 to 1. 3x minus 4. Is it all right with you guys if I go ahead and do this? Dx plus integral from negative 1 to 1 of 9 over x plus 2 dx. Go ahead and split those two pieces up. And this is multiple choice and it's definite integrals, so I don't really have to worry about my plus c on this. I'm going to do these two pieces completely separately and just add them together back at the end. So this part is much more simple. I'm going to have x squared. I'm going to have to divide that 3 by the 2 minus 4x. I am evaluating that from negative 1 to 1. And so that would be 3 halves times 1 squared minus 4 times 1 minus 3 halves times negative 1 squared minus 4 times negative 1. So that's going to be 3 halves minus 4 minus 3 halves plus 4 and that is 3/2 minus 4 minus 3/2 minus 4. The 3/2 will cancel, and I will just get a -8 for that first part. I'm leaning towards C just for that reason on this problem. I'm thinking it's probably not A or B, but I do need to evaluate this just to be sure, because if it ends up being something we can take the natural log of, it could be A or B. But if I had to guess, if I was running out of time and had to guess, I'd go C right here, just based on this piece. Okay, any questions so far? All right, now let's go over here and work with the second part. You're going to have to use a UDU substitution on this. What would the U be? X plus 2. So DU is just 1 with a DX there. So that 9 is in the way, and I'm going to pull it out front. So when I rewrite this with U's, it is going to be 9 1 over U du. And when I integrate 1 over U, what do I get? Natural log. So I got 9 natural log of the absolute value of U. And that is evaluated from, oh wait, do I have to go back to regular numbers on this? I can just change my limits. So if I put -1 in here, -1 plus 2 gives me 1. I should have done that up here. And then 1 plus 2 is going to give me 3. 3. This is looking even more like it's going to be C. I see the 9, I see a 3. So I'm going to have 9 natural log of the absolute value of 3 minus 9 natural log absolute value of 1. What is the absolute value of 1? Or natural log of 1, sorry. It is 0. So this ends up going away. I just get plus 9 natural log of, don't need the absolute value bars of 3 because it's positive anyway. So 9 natural log of 3. And C, in fact, is the answer. Which is what we were thinking all along anyway, from the first part. If you're short on time, if for example we had like a natural log of 4, natural log of 4 is the natural log of 2 squared, and that 2 can be pulled out front as a coefficient, so we'd have 2 natural log of 2, which would have to multiply by that 9 that was out there. So it could change that number where it's not the 9 right there. You're right. If you're short, I like to finish out a problem because it confirms to me that I do in fact know what I'm doing. But if you're short on time, it wouldn't be a bad idea to